probably is on the way. So please, someone please repeat what was last time so we know how to continue.
Okay, so let me start by repeating indeed some definitions. So we were interested in PAC learning, so probably approximately correct learning, and we were expecting that we have an algorithm which, given some samples taken from arbitrary distribution and some objective functions, with high probability outputs something which is close to the objective function. And moreover, we require that there is a uniform bound that works, which is a function of the probability and the error, and it works uniformly for arbitrary distributions. So let me write this.
So I guess I think we should start with the proper realizable case, because I think it was somewhat a mistake to, to start the last time from the most general definition.
Okay, let's just remind what are the objects. So we have some set X where the predicates are defined.
Set X, let's say that it's just a set of natural numbers, and we have binary functions on natural numbers. These are our hypotheses. And we have some distribution on natural numbers, and we are sampling this distribution.
Yes, just make some notation. So there is a set, I don't know, H or how it was called.
Yes, the set, so...
Of hypotheses.
Yes, we have a class of hypothesis H, which is composed of functions from natural numbers into 0 or 1. And we'll say that is PAC learnable if there is a function A, which is called a learner, and it's supposed to take a set of natural numbers with values 0 or 1 and output some function from natural numbers to binary set. And we require that A is such that there is another function M, which takes natural numbers and outputs natural numbers, and we'll call it sample complexity. And the function is such that for every distribution D on natural numbers and function F, if we sample S of size at least M of n, then we have the following, that the probability with respect to the distribution of so we first look at something that the generalization error, so the expected error of the function that is output by our learner. And we want to say that it's almost as good as the best one in the class H. So we then look at all the H in big H. We look at the expected error of H. And we allow for some, this approximates, so we have some error here. And we want this probability to be big. So we have 1 over n here. And this is what we expect. And now there are several subtleties. In classical theory, it's usually assumed, I think the usual definition is that the function A, our learner, is supposed to output also functions from H. But in the classical setting, this really doesn't matter, because if there is a function, then there is a function which will output something from H. But in the computable setting, so if we want H to be computable, then this changes dramatically. And we already saw last week that there is H. So I will say we're saying that if A outputs only things from H, then we will call it a proper learner. And otherwise, if it's allowed to output something from outside the class, we will say that it's improper. So there is an H, which is PAC learnable, but not properly by computable learner. So in the example that we are discussing, the thing that was happening was that we couldn't effectively decide whether a good function for the samples that we are seeing is in our set of hypotheses or not. So because our set of hypotheses was kind of weird. So, but we could see, because all these hypotheses had finite support, there were zeros almost everywhere except at most 2 points. It would be easy to come up with a function that would be good. And if we allowed the learner to be improper, then we could say that this class that's from the example would be computably learnable, but just improperly. So the question is, first question is whether improper learnability is different. Improper computable learnability is whether it is different than just classical learnability, because, and one thing that we will try to see is that even if we allow for an improper learning, there will be a class which is learnable by non-effective learner, but not by a computable one. And to this end, we considered last time this no free lunch theorem, which told us that for every learner, and every n, there is a sample S such that the size of S is 2n, and a function f, and well, sorry, I wrote something stupid. So of course, that's this. I want to say a probabilistic statement. So there's many samples for every learner. There is and n, there is a distribution d, and function f, such that if we sample S with S of size 2n, then we have that probability with respect to d of the error, the expected error of our learner and the expected error of the function f, they are big, they're far away with quite big probability. So the difference between the expected error of what our learner says on S and what the function says is greater than, say, 1/7 with probability bigger than 1/8. So this shows.
Sorry, let me ask again. I'm lost. So
yes.
So you want to construct a class which is learnable but not computably learnable, yeah?
Yes, exactly.
So just imagine we take a class which consists of one function. Then probably this class is learnable by definition, yeah?
Yes.
Yes. Well, if it contains if the one function that it contains is computable, I suppose. But
No,
we cannot.
No, it's just learnable in classical sense.
Yes. Okay. Sure. Okay.
Learnable, but not computably learnable. So it's natural to take one very bad function and it will be learnable with this class. Yeah?
Yes. But the point is that we want to explain something more strong, that there exists a class which is PAC learnable in a classical sense, but it's not computably learnable even if we allow to output something outside the class.
Okay.
So then
if we take
this simple counterexample doesn't necessarily work.
But let me check my understanding. So if we take a class of one function, it's always classically learnable. It's not a problem.
Yes. Yes.
And what about computable learnable? When it's computable learnable, what do we need for this function to be computably learnable?
So if the function is, well, then there are it depends that whether you're computably properly learnable or improperly learnable.
Okay, so what are the requirements for the function for both notions?
So the requirement for proper is just that this function is computable. Then you can just output a Turing machine for that one function always, and that
and if it's computably learnable, it's computably learnable only in the case when the function is computable, or it's just
yes.
efficient.
Well, if in the proper case you have to output computable functions, the learner is computable if it given a sample outputs a Turing machine which computes its hypothesis, its out.
No, but
by definition,
still it's not necessary to in proper case you need to answer something in H.
Yes. So
but in improper case you don't need to answer something in H.
Yes.
But so what are the requirements for the function to make the class.
And yeah, I mean, there is a general characterization that we can state, I guess, as a theorem. Not only in the case when there is only one function.
Okay, but for the case of only one function, what is needed? So for example, if the function is just a Martin-Löf random sequence, then it will be learnable or not?
No.
So it will give the example you want or what?
Yes. But it requires some...
Sasha Kazachinsky, I don't understand something. So what is here L, D, F of F?
Well, it's zero, to be honest.
Okay, it's zero. Assume that the distribution has the property that every natural number has a positive probability. Then any sampler, even if improper, should output exactly F. Otherwise, its quality is worse than zero, right?
The quality is worse than zero?
Or you allow for the case when H consists of one function, you still allow to output something different from F, assuming that it is close to F, right?
Yes.
That's the
yes.
I see. Okay, thank you.
So as Sasha said, taking a Martin-Löf random is enough, but we have to go through exactly through what I'm just presenting to perhaps see that we.
So maybe let's say the theorem when it's improperly learnable something, because it's like the theorem that it's improperly computable learnable if and only if its effective VC dimension is fine. And then we can, and then the condition will be clear, and then we can try to prove this theorem and something.
Yeah, okay. Okay, so we will. So we have this to recap. The VC dimension is we take. So we have the notion of shattering. We take a set of points, and we say that the class of hypothesis shatters this set if every binary labeling on these samples can be realized, and the VC dimension is finite if the size of the sets that are shattered by H is bounded, and that's exactly the VC dimension, the bound. Or if it's not unbounded and we can shatter unbounded arbitrarily big sets, then we say that VC dimension is infinite. And to remind, the classical observation tells us that the classes have finite VC dimension if and only if it is PAC learnable. So now, as Sasha said, we can have a similar we can have an effectivization of this theorem. So we won't only require the VC dimension to be finite, but we also want to have a computable procedure that finds that if the VC dimension is finite, it finds as a witness, namely a set of points such that a certain function is not realizable there. So to be precise, we'll introduce a notion of k-witness, and this is a function
for some class.
Yes, for some class, for H is a function which given x1, x K outputs F such that there is no hypothesis in H which would say exactly the same when we apply it to these points.
So the dimension is less than k. This means that for every k points, there exists some impossible combination of values. And now we require this impossible combination of values to be explicitly given.
Yes. So we will, of course, we will be interested in computable k-witnesses. So we want this function to be computable, and then we get the characterization that a class H is computably PAC learnable if and only if there is K such that there is a computable K-witness for H.
And yeah, and learnable in the improper sense.
In the improper sense, yes. Yes, so because for proper case, we don't have exactly such characterization. I mean, we can have such similar characterization if we add additional restriction for the learning, but that maybe is for
proper case and improper case is again what?
Proper if we output only functions from
you
H.
output only functions, yeah.
Yes.
And learn it's enough to learn function from H, or you want to learn every function as good as if it's possible in H.
Yes, every arbitrary objective function we can and we want to find something that's as good as something in H.
But the equivalence will for both cases will be true, or only for it's important.
It's important that that's for all
if you
objective
want
functions.
to learn functions only in H, this is not true. Or if you want computably learn functions only in H, then the statement is not true.
Yes.
So actually, I think that where we are in the realizable case, at least if we consider recursively enumerable class of hypotheses, there is no difference actually between the realizable case in the normal setting and the realizable case in the computable setting. But this applies for, I mean, this is easy to check when the class is recursively enumerable. Not sure about the general case. Probably not.
Yeah, Sasha, I think the answer is that there might be a class which is PAC learnable for when we only have to learn functions from H, but which has infinite effective VC dimension.
Okay.
So that there is no computable witness for any K.
Yeah. Okay, and then another question, which about the other side. So usually we know that if the VC dimension is less than k, then and we take some number m, and look how many possible combinations exist for values in m points when m is larger than k. Then there is an upper bound which grows somehow polynomially in m.
Yes.
The very important property of the Zauer lemma or something like this.
Yes.
Yeah, and that's in particular gives you that if you take a Martin-Löf random function, then it's not even improperly computably learnable.
Yeah,
by
but
that theory.
the question is if you have this effective k witness. So for every k function, for every k points, you know what is impossible at this k points.
Yes.
Does it imply that you can have the effective Zauer lemma? So you can have a list of a small polynomially sized list of possibilities, which include all the possible behaviors of H.
Yes.
Yes, because we have a learner, so we can just simulate different distributions.
No, it's much simpler. If you have a witness, you just run all strings and see which them agree with the witness. So you have to you just list all functions such that it disagrees with this witness function on all tuples of length k.
Oh,
and you can list them
so
effectively, and by
if you-
Zauer-Shelach lemma, its size is polynomial of this list.
Yeah, so you just exclude something which has a wrong behavior at some point, and that's enough at some k point, and that is enough for that.
Yes. So it means that the complexity, you take, let's say, anything from our hypothesis class which has this property, let's say on the first n natural numbers should have complexity logarithmic in n.
Yeah.
And this means that if I have something Martin-Löf random, then it cannot be improperly PAC learnable.
Mm-hmm. Yeah, okay. So this is your main theorem, or one of the main theorems. Yeah.
Yeah, it's one of the main results.
Okay, so you now want to try to explain the proof of the theorem, or to state other main theorems.
Well, let's focus for a moment on the proof. I won't go through all the details, but the general idea I can definitely give.
Yeah.
So the first implication is already stated. The sketch is already stated above. So we know that we have this. In which direction? That if class is learnable, then we can find the witness. So if we know that if there are too many, if the VC dimension is infinite, then we always can find the function which makes our learner bad. So and this, if we look at the if we look at the proof of this so-called no free lunch theorem, we would observe that we can actually say that if the learner is computable, then we can find this bad function f computably. So the idea is that now, suppose we have a learner. If we have a learner, then we know that the VC dimension, we have a computable learner, we know that the VC dimension must be finite. So there is some k where we don't shatter anything anymore. And then for each points, we can look for this for the BAT function. And when we find the BAT function, this just gives us something that cannot be in our set of hypotheses. And then we output this as a value of the witness.
So you get a computable witness, but for bigger values of k, yeah?
Well, for at least k, I suppose.
No, for some k, I don't know.
For some k,
What
yeah,
do you
yeah.
remember?
Well, for some k, that is bounded by VC dimension from below.
So if you have a class of function, you have some kind of its VC dimension and computable VC dimension, which can be finite by bigger than
Yes.
normal one, yeah?
Yes, arbitrarily large difference between them, I suppose. So do you want to add something, Sasha?
Yeah. I mean, I just wanted to tell it one more time. So, I mean, so this k actually comes from what? So we have that h is PAC learnable. So it's computably learnable by some learner. And we just, well, and we just take the sample size starting from which our learner, you know, learns everything with precision 100, let's say. Okay.
Mm-hmm.
And then we will say that we will find a learner. So and let this sample size be some k. And then we will say that there will be a computable witness for 2k. So given any distinct 2k natural numbers, we will be able to find something which is not in our hypothesis class on that 2k natural numbers. And the idea is that so we can consider arbitrary objective functions on these 2k natural numbers, and then consider a uniform distribution on these 2k numbers, and then samples of size k. And then when our learner receives these samples of size k, then it's supposed to learn output something which is which has error at most like 100, 1 over 100, bigger than the best approximation in the hypothesis class. But on the other hand, we have objective, we just take the random f, then what our learner, it sees k sample, k values of this f on k natural numbers, and then the rest, the best he can do is just guess, because we take f uniformly at random. It means that basically, I don't know, like for most f, the output of the learner will be quite far from the objective function. But for functions that are from the hypothesis class, it should be very close to it by definition, because the real error, if we take f, which is realizable by h, then the error, the best approximation is 0 in the class, right? Because it's from the class. So we can just find any f such that our learner works bet, gives a bet approximation to f, and this would be not in the hypothesis class. And we do this by just brute force.
So it's just a classical argument plus the observation that the search can be done effectively.
Yeah.
Yeah. Okay, so the scheme is more or less clear, yeah. One should check the details, but some kind.
Okay, so now for the other direction.
Sorry, can you repeat once more? So the theorem is for properly PAC learnable, right?
Improperly.
Improperly.
Yes.
Yes.
But the learner can always be correct in this case.
The learner can be what?
Can output a
corrected.
function that's always correct. Oh, no, it cannot because of
No,
the...
but
sorry,
it's kind of
I got it.
process. We cannot guess.
My mistake.
Algorithm we have, it still has a large probability to error.
Because of the theorem on the top. Sorry. I got it.
So now for the other direction, suppose that we have a learner. Sorry, we have a k-witness. So our goal will be to construct something that's well, a class of hypotheses which will be learnable in a proper sense, and which will be a superclass of our initial age. So to this end, we'll consider a class of hypotheses such that so we will take a class. We'll take classes which are defined non-zero on some prefix of natural numbers, and we will ask that if we look at this prefix, the function, and take any k distinct numbers on this prefix, then
So
our
why you need to have a bigger class? What is the goal?
So once again, we have some class that has computable k-witness.
Yeah.
And we have to show that it's improperly learnable.
Yeah.
And
So
we will in fact show that it is contained in some class computably improperly learnable.
Yeah.
Which is computably properly learnable. And by the way, it's of separate interest that, you know, if I have a class which is computably properly learnable, then its subset is improperly learnable by the same learner.
Yes.
And as a consequence of the argument, we show that this is the only way we can have a computable improperly learnable thing. So now we have a k-witness and we have for now initial class, and we define some superclass with this k-witness, and then we show that this superclass is properly learnable. And to show that it would be properly learnable, we will just observe that we will be able to, given a sample, output a hypothesis which has the least error on this sample.
Yes, so
in this superclass, and has finite VC dimensionals.
So the way we construct the functions is that we take some n. Well, I suppose we can assume that it's bigger than, it's not smaller than k. And
we construct this superclass.
Yes.
So we start with a class with effectively finite dimension, and then we construct some bigger class. Okay, what is this bigger class?
Yes, so we take all h such that for every x1 xk which are smaller than n, h disagrees. So let's call our k witness u. So h will disagree with on these points with at least on one label with what the witness says. So we take the witness, then we apply it to the points. So if you look at every k numbers in the prefix, we know that there is at least one label which disagrees with what k witness says. So this
I don't really understand your notation, because you apply h to k, not to one number but to many numbers. But probably what you mean that we have something. So for each k points we have some forbidden behavior, and so now we construct our function which are allowed, but do not have this specific forbidden behavior, which is forbidden.
Exactly.
But up to n.
Up to n. We only do it on the prefix.
Yeah.
And after n, they should be equal to 0.
Yes. After n, we only n h outputs only 0. So we do it as Sasha said. Our goal is to be able to, when we see some points, we want to be able to compute what is called an empirical risk minimization. And in general, we are not always able to do that. But here we only can observe a finite number of behaviors on a finite number of samples. So we can compute all the possible errors and get the function with smaller error because of what's happening here, of how it's defined. So we take this class, and indeed if we see a sample, we just look at all functions which are see a sample S such that the biggest number in S is.
Sorry, is the class of definition of the class clear or no?
Definition or construction?
No, I don't think so, because I think that from the definition of this U, it follows that the class contains all H.
So U is a witness here.
No. Of course, this new extended class contains all the original H's, but it also.
Yeah. So the idea is that we have original class, and then we add all H's that satisfies this condition for some n.
I see now.
So the condition is that, well, basically the function has finite support. Well, so for some n, so after n, starting from it, it has only zeros, and if you look up to n, then it doesn't have a forbidden behavior, which is given by you.
Yeah, but if you require it to be finite, have finite support, then the original class is not a part of it. Yeah.
Yeah, but we just add these functions to our original class. And then we obtain a superclass.
Okay, so I have a question, but it's kind of side question. But maybe Laurent, you can say something. So imagine we have a math problem. So for every 10 points, we have some behavior of the function which should not occur at these 10 points. And this is probably well studied, and it's known that this is in reverse mathematics is something or that or this or that. Does it have? Is it some kind of known things?
Well, you'd have to specify more precisely the math problem that you want to attach to this, right?
So imagine we have some kind of I don't know, for every 10 points, we can compute some behavior which is not possible at this 10 points.
But here they're
Because
just
what
your
do you
one
mean
value.
by this is not possible?
Right, but these are just your one values, right? Your point here, your points are what? Your points are integers, and
Yeah.
and
So
the values is
and values are 0 and 1s. So for every 10 points, we have some combination of values which are not allowed.
yeah, but so it's a math problem into what? Like into a class of possible hypotheses?
No, so we have an effectively closed set of infinite binary sequences which avoid all the prohibited behaviors.
It's a finite set of points. You can always
No, finite set of it's a set of sequences.
that's your class. You have a class of hypotheses. Yeah. Math problem is just about just outputting one element in just one class. Here you seem to parameterize it somehow. Or
so we have some computable function which says which combinations of 10 values are forbidden.
In the class.
Which combination? So
One specific combination which is forbidden. We just for every 10 points have one specific combination which is forbidden. Then
sure.
First question is completely stupid. Is it possible? Is it always non-empty? Or can we always avoid all the restrictions?
Well, certainly for some Python classes, there's some like if you want forbidden things, you'll get an empty class. Surely.
But we are not allowed here. We forbid in some very restricted way. So for 10 values, we forbid only one combination.
Yeah, but it's still got to be empty.
Okay. Maybe okay. I thought that something well known which I just forgot. But okay, if it's not so obvious for you, but then okay. Sorry.
No, I don't think there is much.
No, it's a bit like Lover-Schlocker lemma, but one should.
So, but Sasha, what if I just first I make forbiddens that disagree with all finite support functions? So I can, by that I can just well, I don't know if it's always empty. I guess that it would be empty.
Whether it's possible to forbid all the behaviors just by prohibiting behaviors by having this witness. Is it possible that for given witness there is no function which?
Well, if we have just one, then we cannot do that because if our witness is just on, we prohibit something on just one point, then we can take something which is not prohibited, right?
No.
But if you prohibit something for pairs of points,
Just very stupid question. Can we prohibit everything by prohibiting one combination for every pair of points?
Yeah. Okay, yes, I think yes. You can consider 4 points. You can prohibit 0, 0, 0 on the first two and 0, 0 on the second two. This means that you can the first two and the second the first in the second and the third and the fourth must have at least 1, 1.
And then you prohibit 1, 1 on all.
Then I prohibit all pairs 1, 1 in the in the, yes.
Yeah. Okay. So it's a stupid question. Just sorry for interrupting. Yeah.
Yes. Okay. I mean, we have discussed this question at certain point. I don't really remember the details now, but I think that actually 3 points would be enough. That you just have to have one more than the size of the points that you are forbidding. Well, but that's on the okay. So we take this class, and now there is one non-trivial observation from classical theory is that well, if we look back,
I think it's now not so hard to finish the proof, because we know that the VC dimension of larger class is at most k, or is less than k, right?
No, it's less than k plus 1.
yes.
Yeah. Okay. And then we know that empirical risk minimizer will be a witness, and we just have to understand that means just a learner that outputs any function from the class that makes minimal error on training set, minimal error on x1 till xn. And so we
Sorry,
just
Bruno, but can you the fact that it has bounded VC dimension is not, it's easy, it's simple, but it's not completely. Can you say why it has a
because VC dimension means that for every k labels we have all possible functions, and we said that even computable function tells you one function you cannot make from H by definition of k witness. VC dimension.
But here we had functions that might disagree with k witness on after n.
Oh, sorry. So we add functions that might disagree with k witness.
They disagree with the witness up to n for some n, and then they are equal to 0 afterwards. And after n, there are no requirements for tuples that include numbers starting from n.
So, if we think that the points larger than n do not exist, then it is easy. And so the only problem remains for points for value larger than n.
Yes.
Okay, but they're unlikely to be sample test point. If you
But I mean, it's just the claim is that the VC dimension of this thing is at most k.
Yes.
So given any k plus 1 points, I can find something which is not realizable. So one more point you need to find something that is not realizable.
Okay, I will not say anything anymore.
No. I mean, so the point is that if I have k plus 1 points, I can something which is not realizable is something which is equal to 1 on the last point and is equal to something forbidden on the previous k points.
Ah, okay, yeah.
So that's just because if I even have this function that I added, and if it has 1, then this one must be before this n, because after n we have only zeros. So although we have k witness, which means that we start with k witness, which is supposed to be witnessing that the VC dimension is less than k. For this larger class, we get a witness that just witnesses that the VC dimension is less than k plus 1, but still is finite, so there's no problem.
Okay.
Yeah, and then the rest what remains to do is to show that if I have a sample, I can computably find something in this superclass which has the least error on this sample.
Yes, but I mean, there is also a non-trivial fact from the classical theory, which tells us that if we have a finite VC dimension, then the empirical error, so what the errors that we see on the samples are with high probability close to the generalization error. So, and this is basic. This is this combination of two observations. So one is the Hevding inequality, and another is the Sauer lemma, which so the fact that if the VC dimension is finite, then the number of sets that we are shattering grows polynomially, and then we are still able to apply the Hevding inequality, even though the number of possible behaviors is not finite.
So you mean that you just say how the classical proof of learnability of class with finite dimension goes? It's a combination of Sauer lemma and Hevding inequality.
Yes.
So Sauer lemma says that something is polynomial, the class of possible function is polynomial, and the inequality says that the frequency should be close to probability or something.
Yes. So suppose that we have only one hypothesis, then we can just take this one hypothesis and take the treat the empirical frequency as we have a variable of probability of making an error. So we have expected error, and we compare it to the empirical error. And by Hevding inequality, we know that if we see n samples, then the probability that these two values are bigger than t is this x to 2 square over 2 times n or something like that. So this works for one hypothesis. If we have a finite number hypothesis, we still can, because what we want to get again is this, if we look back at the definition, what we want to get is this function m of n, which tells us that if we see at least m of n samples, then with probability 1 minus 1 over n, our error is close to the best one up to 1 over n. So this we can get from Hevding if we consider one variable, or if we consider y hypothesis. Or if we consider finite number of hypotheses, then we just take the bound from Heffding that many times as many hypotheses we have. And still, if we take the sample to be big enough, we can satisfy similar bound like here. But the problem is that our class of hypotheses can be infinite. So, and this is a little bit hand waving, and the exact proper proof is more involved. But what we want to notice is that first, that in fact, even though the class of hypothesis is infinite, if we take n samples, then the number of behaviors on these samples is somehow bounded, and it's slowly growing as a function of n, which allows us to still have a nice bound from Heffding, even though we have infinitely many, even though we are kind of considering infinitely many variables.
So, but can you summarize then what the learner is doing? So we know this forbidden.
Yes. So in the general setting, okay, the learner just if we don't have any effectivity assumptions, then we can just say that if the learner sees samples, he looks at all the hypotheses he has and tests all the hypotheses on the sample set and on the empirical data, computes, well, he checks what is the empirical error and outputs the one that has the minimal empirical error. And we do that for as we get more samples and more, this is what we do. And since we know that if we see m of n samples, then our empirical error is close to the generalization error. So here in the definition, we can indeed put we can take 2 over n, I suppose, and instead of n, so 2n instead of n, and instead of L df A of S, we can put the empirical error.
So, but you explain some argument, but what just the learner does? So imagine we have...
So the learner just, the classical theory says that you take any learner which outputs a hypothesis which with the least error on the sample, this learner learns.
Yeah. So here we also...
The problem is...
Also, we can, given a sample, we can take all hypotheses which do not contradict this forbidden behavior, and take the one which is closest to our sample.
Exactly.
Yes.
And because the VC
but the point is that why we added these functions, because we can just output. So we have a sample and it has it was numbers up to n. Yeah, and then we can output. We can just look at all what we can have on this first n natural numbers with which disagrees with the witness on this n natural numbers. The point is that we don't have to output something. We don't have to like compute some function which extends this and disagrees with the witness after n, because we have these functions that disagree with the witness only up to n, and then are zeros anywhere elsewhere.
Mm-hmm. But if you define learnability just in the way that you need to predict a value at one new point, then you won't have this problem.
Well, I'm not sure if I am giving you some value in some new point after n, whether this will be extendable to something,
No, if we don't require to extend anything, you just learn in the sense you are given sample, then you're given one test point, and then you need to produce answer, which would be, in my opinion, a more natural way of learning. But okay, defining learnability, but it seems to be equivalent because of Markov inequality. Or not?
well, then I don't know why it's not clear why this thing, if you just find something which predicts and you're just interested in, it's not clear why it learns. Here to show that it learns, we show that it's inside some class of finite VC dimension. When your prediction
Well,
exactly. What? So you are given a sample, and then you are given the next point. What we are doing?
but we are sampling the next point, or is it just given by an adversary? Because I think that's
We sample. We given the
point.
next point from the same distribution.
Well, but isn't that what we are effectively doing? Because we just, well, we have our hypothesis is just a behavior of what we will do. We can take a hypothesis and we ask for a generalization error. So we basically ask, we give a strategy which, given a random sample, outputs something.
Okay, probably I just no. You are accustomed to all this classical. Yeah. You say this generalization error, this error, that error.
Yeah,
no,
sure.
But I guess something simple is really happening. But okay, but so yes. In general, you just combine the classical argument, whatever it is, with some simple computability observations. There is no special point when you need some new specific or very different new argument to switch for classical case to effective case.
Yes.
Yes, I think so. I agree.
Mm-hmm. Okay. Then the promise that if and when we learn the classical argument well, then we should understand also that it's computabilizable.
No, Sasha. I mean, the computer. You don't need to understand. So you don't. You just need to understand something from the from the argument, but from the statements. From the statements that you just have to output something which has the least error on a sample, and this learns if provided that the class has finite VC dimension. And then in this case.
So you say
we are able to do that because we added functions
not use
where we don't care about continuations.
So what you say that we may just apply the classical result, not going into the proof, or what?
Yes.
And we apply it to the bigger class, which contains the special things.
Yes.
Mm-hmm. Yeah. Okay. No. Some general picture I think we have, but about this result.
Okay, so I suppose we have still a bit more time.
Yeah, we have a bit of time. You can explain your other results if you want.
Yes. So there are two things that comes there. I mean, there are several things that we could say. So one is given that we have this characterization with k-witness, we can easily come up with an example of a class which is not learnable, and this class might be even decidable. And well, okay, maybe to get more accustomed with this, let's try to do that. So I will show a class. Well, maybe for started, we'll start with the easier case. So I will show that this is a class which is recursively enumerable. Recursively enumerable class H, which
of computable functions.
Of computable functions only, which is
with finite support, I guess. So it makes, then it's clear what does it mean that it's recursively.
Yes, so the classes are with finite support. So to define each class, we only need to state a finite number of numbers where the values are 1, and everywhere else they are 0.
Yeah.
So these are just finite words, and it's recursively enumerable in the sense that we can enumerate the sets of these supports. So there is a class H which is PAC learnable, so it will have a finite VC dimension in the classical sense. But it is not improperly.
Okay, but just forget about PAC learnability. It has finite VC dimension, but not effectively finite VC dimension. Yes.
Yes.
Yes, exactly. Yes,
Yeah.
that's the other. Yes, because that's the only thing we will really be interested in. So the idea is that we will take as this is perhaps something I shouldn't need to explain, that the k-witnesses are total functions, and we cannot have an enumeration of total functions, but that's not a big problem for us. We can take an enumeration of effective enumeration of all computable functions. Well, phi of Turing machines. And
what is it? It's VC dimension, classical VC dimension.
1.
1 means that.
I mean, we didn't define it yet, but the answer to your question is 1.
So 1 means that for every point,
For every 2 points, you can implicate something which is not realized.
Yes.
Mm-hmm.
And it's just you diagonalize again also possible witnesses.
Yes. So
if you have a witness, you add a hypothesis which agrees with him on some tuple, and you take it for disjoint tuples for different witnesses.
Yes, so we just partition in the natural numbers in these segments, which are of different length, because the length will correspond to the size of the output of phi I. So this is something we can also hard code in the machines. And well, we enumerate all the machines, and we run. We have these intervals I1 and I2, and we run Fi on the inputs for the inputs of numbers of this interval. Well, and if we see that one of the functions halts on the interval, then we have a hope that this machine computes some potential k-witness. So if it's something that could be a k-witness, then given these numbers, it will output a binary string of the same size. If that really happens, then we put exactly this string on the interval. So if
sorry, but before you prove something, can you tell us what is H? Because I don't understand it.
H?
What is the class H?
No, we can
class of hypothesis.
by the diagonalization. So for every possible candidate for witness function, we add some function to H, which makes this candidate doesn't invalid.
Ah, okay.
So we just add some function which behaves some in a forbidden way in some specific place. And we even don't try to interact between the requirements. Each requirement has its own place. And the
yes, exactly. So if this
is whether all the dimension will not be too big because of this.
Yes. So if this guy stops and outputs x binary x of size I, of some size si corresponding to this interval, then the function that we are getting is something like 0, 0, 0, 0, 0 until we get to interval I, and here we put x and then 0, 0, 0, 0 again. So every hypothesis has a corresponding interval. And it's the only place where it can have ones. Some functions correspond to machines that never stop, so then we just don't add the function. So
okay, and one more time. So H contains only one function. Is it right?
No. For
every possible candidates, we either do not do anything or add one specific finite function to make this candidate non-working.
Yes, like here on the picture, like we try to take a function, a enumeration of machines. We think we guess that the machine is maybe a k-witness for some class of hypotheses, and we apply it to certain interval. If it stops, then on this interval we put exactly the labelings that the machine gives us. This means that this machine, and then we add zeros on the left and zeros on the right, and this is our hypothesis which we add to the class. This means that this function cannot be a k-witness for our class because we already have a hypothesis which agrees with what the function says for this interval.
Okay, and the VC dimension is 1 because functions are only non-zero in these joint parts.
Exactly. Yeah. So we cannot realize the best we can hope is that we have an interval where we have something which is 1, and then for every other functions it will be 0 there. And so this is only the size that we can shatter.
Okay, and now you want it make recursive or what?
Yes, so I will now argue that we can in fact make this decidable. So how could we do that? Well, instead of adding a functions, if the machine stops,
leave some places free to make the number of counterexample infinite, and then took the more advanced counterexample if the computation takes a longer time or something like
that. Exactly. So we will have we take the odd numbers and odd numbers. We will do exactly what we did in the something that we did in the previous case, and on the even numbers we will encode the numbers of steps of some machine. So now we'll look if I stops in M steps.
No, you just have to postpone the adding, and then you add something big to this function, so you can check this in and so you get some artificially recursive. Yeah. I think it's so you don't need to make any diagonalization, serious diagonalization, which takes. You never need to consider two forbidden things at the same times. So you deal with each of them separately.
Yes,
Yeah, exactly.
this is a very simple argument.
Yeah. Then I think it's clear. Yeah.
There is also a nice example. So when if you take the halting set and as an infinite string, you can also show by this argument that it's not improperly learnable, just one function, computably learnable. So there doesn't exist this k-witness function. There are even two arguments, one with time-bounded Kolmogorov complexity, and the other is
So say it again. So there is a halting set, and you say that that's not possible for n elements to say something which is forbidden.
Yeah. Or like in the other way around, you can. So there is one result that says that, well, okay, if you consider prefixes of the halting set, then its Kolmogorov complexity is logarithmic because you can just enumerate it. But there are results that there is no time bound, which makes the Kolmogorov complexity logarithmic.
Yeah.
And
and actually we can have it for more than just prefixes. So we can have that if we have a numbers x1 to.
No, it's pity that Laurent left because I guess it's just a classical recursion theory that there is no way for a given n programs to say which behavior is impossible for them to terminate or not.
It's possible to explain with just classical theory. It's just you need fixed point theorem that like n-fold. So if you have n programs, you can and you have a computable transformation of it to other n programs. There exists an initial programs such that in the result the programs after transformation compute the same functions.
No, okay, because you can consider n program as one program for n points. So it's in and then you cannot make them different.
Yeah, and then what you say that why isn't possible to do this? Well, on the other hand, if you can output something which is disagrees with the halting set on this n natural numbers, it's more or less the same as saying that you can solve halting problems correctly for at least one of n programs. because you can just inverse your answer. So, and then the question is why it's impossible to, if you have n different programs, to solve the halting problems correctly, at least for one of them.
No. Okay, it's something which would be called DNR or something like this, but this Laurent should explain, but he's not here. Okay, let's think it's a good homework because it's easy, and I think we will all enjoy it while yeah. So any other results? Maybe
Well,
you.
Yeah, there are other results, but I don't know. We don't really have time now.
yes, to go into details.
There are like results about the case where you computable, but you have to output something inside the class.
Yeah.
And there was an open problem whether you can always achieve a computable sample complexity. If you can learn something in the proper sense with maybe some very, very bad sample complexity and computable, whether you can turn it into the computable sample complexity with some other learner. And the answer is no.
Okay, and did you study, or not you, but somebody else? If you require the predictor to be reasonably computable, like polynomial time or something like this, it's probably also studied or not?
Yes, there is a book by Vazirani and Vapnik, and Vazirani and another guy with the V called Computational Learning Theory.
Another Vazirani.
From the 19th. Yeah.
Well, Sasha, I think there are like more specific results. Like you have DNF, you want to learn DNF, and there are lower bounds and upper bounds. Not like in this or you can learn decision trees and so on that.
So you say that if you want to have a polynomial time learner, then this VC dimension is no more a crucial point. That's general picture, yeah?
Yeah.
Yeah, so there are like results that I don't know, polynomials should be polynomial time learnable. Because actually, you just have to find a polynomial.
Original definition by Vapnik from 1984 requires the learner to be polynomial time. But then many different people made their own variant of the definition, like dropping the running time. And also, for example, there is result if you believe in RSA cryptography, then you cannot learn finite automata of certain size k and time polynomial n k.
Specifically RSA cryptography, not just one-way function, but
yeah. The first reduction was so if taking discrete logarithm you cannot do in polynomial time, then and the idea is to program somehow automata that compute multiplication and so.
Oh.
Yeah.
Oh.
It's the oldest result, but there is a huge amount of result. There is even a conference called Computational Learning Theory.
Called.
Yeah, called. But they now more in machine learning.
So you send it not to cold but to alt.
No, we send it to cold.
No. Yeah, but I think cold now also more focuses on theory of machine learning.
Mm-hmm.
Yeah, it's really nice, and so there are like it's NP hard to or some cryptographic weird cryptographic. Yeah, I forgot. I cannot tell the names now, but it's just like hundreds of very interesting papers
And-
about when it's possible and when not. For example, learning half spaces is NP hard. So PAC learning of half spaces. So in agnostic setting is NP hard.
Mhm.
And the latest, so there are like 30 papers to prove this, and each time making the results stronger and stronger. And now it's ridiculously strong. So even to find half space that is better than so even the approximation hardness, this NP hard to approximate the best half space classifier. So given a data set, it's NP hard to tell whether the best half space classifier is 0.49% accurate or 0.01% accurate. It's the state-of-the-art result from a few years ago. I forgot who is the author. I don't remember.
But maybe you can then give an explanation talk when you will prove some of the simple results of this type and what is, so to get out some feeling what is happening in this learning theory.
You want about effective PAC learning?
Just something which you find interesting about effective PAC learning, or also there was something, maybe you know this. There is some algorithm which is called learning algorithm, which is called WinNow, WENNOV. And I remember a paper of which was used for Kolmogorov complexity and dimension or something like this. But maybe it was very old paper. But if you know this, maybe you can.
Yeah. I started to read this paper about Winnow algorithm, but it's about online learning. It's a different field. There is no probability there, but it's also useful for the general setting. But it's all kind of connected. But this, yeah.